When you force a single language model to handle research, analysis, and formatting all at once, the system fractures under the cognitive load. A massive, unified prompt dilutes the context window. As the model attempts to switch between highly disparate subtasks, its reasoning degrades, memory is dropped, and output reliability plummets. The architectural solution is to abandon the single monolithic prompt entirely and divide the workload across isolated, autonomous entities. CrewAI is a framework designed to build exactly this, segmenting complex workflows into networks of highly specialized agents. The first layer of this framework is the foundational node, defining and fine-tuning the individual agents to perform a single, narrow function. The second layer is orchestration, linking these specialized agents together into structured execution topologies, known as crews. The final layer is integration, wrapping these crews within programmatic, event-driven state machines, known as flows. Transitioning from unpredictable text prompts to deterministic multi-agent state machines is the mandatory requirement for building reliable, production-grade automated pipelines. The baseline computational unit of the CrewAI framework is the agent. To initialize a functional agent, you must program it with three specific attributes: a role, a goal, and a backstory. The backstory parameter functions as strict contextual tuning for the underlying language model. It assigns a precise professional persona that dictates how the model processes information. A generic request to search the news will generate broad, surface-level results. Assigning the backstory of a cynical investigative journalist forces the model to apply a highly skeptical analytical lens to that exact same search task. Establishing this persona bounds the model's analytical depth and governs its internal logic when selecting which external tools to deploy. With the persona built, the agent requires a distinct execution target. This is the task. A valid task within the framework requires two strict components: the description of the work and the expected output. Defining the exact format of the expected output establishes a terminal condition for the agent. Enforcing this strict formatting prevents the model from entering open-ended processing loops. It gives the system a verifiable endpoint to prevent uncontrolled hallucinations. Combining a strictly defined persona with a precise task output transforms an erratic language model into a reliable, deterministic processing node. To utilize these nodes effectively, they must be given a coordinated execution path. This macro orchestration layer is called the crew. The default execution topology is the sequential process. Node A executes its task and injects its raw text output directly into Node B. Nodes can also query peers or divide subtasks if allowed delegation is enabled. However, a rigid sequential path breaks down when applied to highly complex projects that require dynamic reasoning and nonlinear data routing. For complex environments, the framework deploys the hierarchical process. Tasks are fed directly into a central language model manager, acting as the system's brain. The manager analyzes the available workers and dynamically allocates tasks to the most qualified nodes. The manager also maintains oversight. Instead of allowing workers to blindly pass data down a pipeline, the manager evaluates all completed work. If an agent returns hallucinated facts or logically incomplete data, the manager catches the error and triggers an automated revision loop, forcing a correction. While sequential processes excel at predictable routines, hierarchical processes are mandatory for automated error correction and dynamic resource allocation. Pure language model crews share a critical vulnerability. They lack procedural rigor, permanent memory, and native integration with traditional enterprise codebases. To solve this, crews are encapsulated within an event-driven Python architecture called CrewAI Flows. Flows use Python decorators to trigger execution based on system events. At start establishes the workflow's absolute entry point. At listen forces a method to wait until a prerequisite process finishes. At router evaluates logic conditions to choose between branching execution paths. Moving complex data through these steps exposes another vulnerability. Standard agent setups frequently lose track of variables across multiple handoffs. Flow state management solves this data degradation by maintaining a uniform, persistent state object throughout the application's entire lifecycle. You can use flexible, unstructured dictionaries for this state, but production environments require the safety of structured data schemas. Pydantic data schemas enforce strict data types, protecting the workflow from unexpected breakages caused by erratic LLM outputs. Finally, flows utilize a built-in SQLite database backend to guarantee state persistence. If a script crashes, the system can instantly resume execution right where it left off. Flows successfully encapsulate unpredictable language model intelligence within a deterministic, fault-tolerant software architecture. We can now trace a task through the complete production-ready architecture. At the foundation, agents execute specialized analytical intelligence, tightly bounded by their assigned personas. Above them, the Crew orchestration layer dictates the routing topology and enforces automated quality control. And in closing the entire system, flows enforce deterministic execution logic and guarantee permanent state persistence. True enterprise AI orchestration requires balancing the emergent problem-solving capabilities of language models with the type-safe, event-driven constraints of traditional programming frameworks.